This talk is called Gibsonian Information, Agent-Based Information Theory, with co-authors Bradley, Alicea, Daniela, Cialfi, Avery, and Jesse Parent. So one way to define Gibsonian information is to contrast it with Shannon information. In Shannon information, it's variety that provides information. It's the probability of one state in a set of states, its structure versus randomness. Stated briefly, you have an encoding that gets embedded in a binary channel with noise. You get a decoding, which provides the information. So efficient transmission of a signal over a noisy channel results in expected versus unexpected configurations of a system. So basically, if you have a lot of states, you end up with very little information, but if you have only a few possible states, you end up with a lot of information. Gibsonian information is a bit different. In this case, motion provides information. So it's real-world things like optical flow, relative motion between the object and the observer, and structure from motion. Stated briefly here, you have this external communication channel, which are a bunch of objects that are distributed according to a Poisson distribution. They're transduced into an internal communication channel, which preserves that Poisson distribution, but adds a temporal lag, tau, and you can treat tau in different ways, but it's basically a very rudimentary internal representation. It's distorted in some way from the external case, and then it's decoded into behavior. So you have highly patterned input. You have a noise-free internal representation with temporal accumulation. So this distortion is basically temporal accumulation, but you preserve a lot of what's going on the outside. And you end up with expected patterns in the external communication channel, and you end up with a minimal noisy internal communication channel. But critically, it's not so much the configurational space that's important in Gibsonian information, but it's the motion space, and it's the continuity of different types of stimuli and its direct perception that's important. So now we can talk about direct multimodal information. So we have this direct perception, and this is an example of a roller coaster, an agent riding a roller coaster. We can use a simulation to look at the multimodal nature of this information. So we have a number of different channels of information here. We have visual, proprioceptive, and probably auditory channels, in addition to motion information coming from different means. The observer experiences this and determines the richness and detail of this information in their internal representation. So this is temporal accumulation network. So I'm going to go through four things that we kind of think about when we think about Gibsonian information that define it in terms of this sort of direct perceptual stimulus. So the first is that flow, motion, and contrast. So you can see this image, you have visual flow, you have motion cues, and you have contrast between the background and the foreground. You also have something called disjoint distributions of information. So this is where you have, say you have a field a Gaussian field of static, and you have moving static versus static, and you can actually look at those two things as disjoint distribution of these different types of information. So an example of disjoint distributions is that you have these two different types of static, and this can be characterized in an equation, and this is very similar to mutual information, although when you have zero mutual information, you have a lot of disjoint distribution information. The third point here is time series structure. So you have this temporal dependence. So these are two videos. One is a full video with action that makes sense. It has full temporal dependence. The other one is where clips have been cut out and put back together, so it doesn't make much sense from a temporal dependence standpoint. Basically, a dependence in time is necessary for full Gibsonian information. You have this concept called contingent action, where each node in this tree has information that the previous node needs to have to be consistent. Finally, we have maximum versus minimum coherent movement. This is where we have flocking and swarming as an example, where the different agents will sort of look at their neighbors and try to not only sort of perceive what coherent movement should be, but also as an output of a behavioral output. So you see coherent movement, each agent has its own set of rules that it follows to sort of participate in this coherent movement. And this can be contrasted with a bunch of balls bouncing around a chamber randomly. As you can see, they don't use this type of heuristic to generate movement. So this is something that is taken from the collective behavior literature, but it's applied this sort of information. Now we're going to talk about an example called 4-channel embodiment, and this involves 4 sensory channels: vision, haptic, proprioceptive, and auditory. And each of these action sequences that will show how the specific modalities contribute to multimodal information. So you have congruence versus incongruence. These signals should be congruent in space, but also in time. And if they're convergent, you have this multisensory multiplicative effect. If they're divergent, you have this multisensory suppressive effect, which interferes with the ability to accumulate Gibsonian information. So follow the white rabbit. You have these 4 channels. They're kind of moving in concert here, and then they start to diverge at the end of the sequence. So you see this rabbit, it's moving. There's visual perception involves forward, it captures forward motion. The haptic sensory channel captures forward momentum. The proprioceptive information channel says that there's a shift left, and then the auditory channel has birds chirping from behind, and all those percepts are put together by the rabbit, and it gives it a certain amount of Gibsonian information. Finally, we can talk about Gibsonian information in the context of the free energy principle. So the free energy principle takes us a step further, takes the Gibsonian information and says that that we can put this in a context of a more complex internal model. So the free energy principle allows us to enrich our internal communication channel. So we can see that we have active inference going on in the example of the rabbit, where the rabbit is taking in information, evaluating information at each time step. Its internal model is accumulating this temporally, and there's some sort of distortion. But in the case of the free energy principle, we're able to smooth out that distortion using different mathematical tools. This also allows us to make links between Gibsonian information and thermodynamics. So for example, we can minimize the energy it takes to acquire Gibsonian information, or we can minimize sort of the interference between percepts that would allow us to increase our amount of Gibsonian information that we have. We can also think of this more in terms of Shannon information, where we look at linkages between informational and physical entropy, and the Landauer principle does this with Shannon information. We'd like to do the same with Gibsonian information. Check out our preprint at the Sci Archive, and thank you for your attention.